Assalamu alaikum. Hello students of class 11. I hope you are doing well. I am Mohammad Mohiuddin Sharkar, your MMS Sir, lecturer in chemistry, English medium morning shift, Rajakuttara Model College. I am here to teach you to stay at home with study. So stay home, stay safe. Now I am going to discuss about chemistry first paper on chapter 4, chapter name chemical change, topic name acid-base equilibrium. In this topic we will learn Oswald's dilution law, dissociation constant of weak acid and base, strength of acid, ionic product of water, pH and pH scale, and finally buffer solution. So let's start. Oswald's dilution law. This law is applicable only for weak electrolytes, for weak acid or weak base. So the degree of dissociation of weak electrolytes like weak acid or weak base is inversely proportional to the square root of its concentration. Again, the degree of dissociation of weak electrolytes for weak acid or weak base is inversely proportional to the square root of its concentration. If alpha is the degree of dissociation and C is the concentration, then we can write alpha is proportional 1 by root C. So we can say if the concentration is lower, then the degree of dissociation will be higher, or alpha is equal to root over K by C, where K is the dissociation constant. For acid, K is equal to Ka. Here K is the dissociation constant of acid, and for base, K is equal to Kb, where Kb is the dissociation constant of base. This equation for weak acid and this equation for weak base. Now the determination of the dissociation constant of weak acid and weak base. This dissociation constant denotes the strength of acid or base. If the value of dissociation constant is higher, then the acid or base will be more strong. So the dissociation constant of weak acid, let us consider a acid, ASA. Here ASA denotes any types of weak acid like acetic acid, carbonic acid, that is partially dissociated in water. At equilibrium, you can write a ASA plus water that will dissociate and form hydronium ion plus anion, or you can use only acid, ASA, that will dissociate and produce proton plus anion. So applying law of mass action for equation 2, K is equal concentration of proton, concentration of anion, and divided by the concentration of weak acid. Here K is the dissociation constant of acid, where this concentration sign denotes the concentration of proton, anion, and ASA respectively. So we can say if the value of K is higher, then the acid will more strong. Now the determination of the concentration of proton for weak acid. Let SA is a weak acid and C is the initial concentration and alpha is the degree of dissociation. So we can write SA that will partially dissociate and form proton plus anion. We know in a reaction, before starting the reaction, the reactant concentration will be higher. That's why the concentration of reactant HA is C, and the concentration of product is lower, and that will be 0. If the alpha amount is dissociated, then the concentration of product proton is C alpha and the concentration of anion is C alpha, and this denotes the undissociated of acid. So we can write K is equal concentration of proton into concentration of anion divided by concentration of weak acid. This is the value of the concentration of this. So, finally we can write K is equal alpha square C divided by 1 minus alpha, or K is equal alpha square C. For weak acid, the degree of dissociation is negligible. That's why you can write 1 minus alpha is approximately 1. Or alpha is equal root over K by C. That denotes the Oswald's law. So the concentration of proton is equal C alpha. This is the value of alpha, and finally we can write the concentration of proton is equal root over Ka C. Mathematical problem. The degree of dissociation is 1.4% of 0.15 molar acetic acid. Determine the dissociation constant of acid and the pH of this acid. So here given the degree of dissociation is 1.45%, and we have to find out the dissociation constant of acid K, and the concentration is given 0.15 molar. So you know K is equal alpha squared C, putting the value of it, and finally we get the value K is equal 3.15 into 10 to the power minus 5. For determination of the pH, we know pH is equal minus log concentration of proton. We know acetic acid is a weak acid, that's why it will partially dissociate. That's why we will use this equation for determining the concentration. So the concentration of proton is equal alpha C. So this is the value of alpha, and this value denotes the concentration. So finally we get this, and the pH value is 2.66. Dissociation constant of weak base. This equation is same as acid. I just used a weak base instead of weak acid. It will dissociate and form B plus and a hydroxyl ion, and the Kb is equal concentration of B plus into concentration of hydroxyl ion divided by concentration of weak base. So you can say higher the value of Kb, the base will be stronger. Determination the concentration of hydroxyl ion for weak base. This is the same case as the concentration of weak acid. So this is this concentration denotes the undissociated of weak base, and this is the concentration of B plus and the concentration of hydroxyl ion. Finally, you can write Kb is equal to alpha squared C, or alpha is equal to root over Kb by C. So the concentration of hydroxyl ion is equal to C alpha. Here this value denotes the value of alpha, and hydroxyl ion is equal to root over CKb or KBC. The degree of dissociation is 1.30% of 1 molar ammonium hydroxide. Determine Kb. Here given the degree of dissociation 1.30% and concentration 1 molar, and we have to find out the dissociation constant of base Kb. So we know Kb is equal alpha squared C, putting the value of alpha and C, and we get Kb is equal 1.69 into 10 to the power minus 4. Strength of acid. We can compare the strength of acid by knowing the value of Ka and pK. So we know higher Ka value, lower pK value is equal to strong acid. In contrast, lower Ka value and higher pK value is equal to weak base. Here I have used two acid, acetic acid and hydrofluoric acid. So the Ka value of acetic acid is 1.8 into 10 to the power minus 5, and the Ka value of hydrofluoric acid is 5.62 into 10 to the power minus 4. Where the Ka value is higher of hydrofluoric acid than acetic acid, and the pK value is lower of hydrofluoric acid comparatively acetic acid. So we can say hydrofluoric acid is more strong than acetic acid because its Ka value is higher and pK value is lower. So strength of base. This is the same case as strength of acid. So higher Kb value, lower pKb value equal strong base, and the lower Kb value, higher pKb value equal weak base. Here I have used two base, ammonia and methylamine. So the Kb value is higher of methylamine comparatively ammonia, and the pKb value is lower of methylamine comparatively ammonia. So we can say methylamine is more strong base than ammonia. Now we can determine the strength of acid based on ionic size. Hydracids, a substance which dissociates fast in solution to donate proton ion easily will be the stronger acid. Again, the substance which dissociates fast in solution to donate proton ion easily, that will be the stronger acid. For hydracid, like hydrochloric acid, hydrofluoric acid, the big anionic size will dissociate fast and donate proton ion easily will strong acid. among four hydrocide, if I ask you which will more strong acid, most students will say hydrochloric acid will strong acid, but this is not correct, because among four halogens, iodide is more bigger size comparatively all other halogens. So we can say among the four halides, iodide, bromide, chloride, fluoride, the size of iodide is largest. In Hi, the hydrogen atom is far from iodine. That's why it can easily dissociate and donate proton in solutions. We know the substance that will dissociate fast and donate proton easily, that will more strong. So that's why Hi will more strong acid. Acid strength of oxoacids based on oxidation number of central atom. Here I use different types of acid. Perchloric acid, sulfuric acid, nitric acid, sulfurous acid, nitrous acid, and chlorous acid. So we know the more oxidation state will be the stronger acid. Here the oxidation state of chlorine is +7, sulfur +6, nitrogen +5, sulfur +4, nitrogen +3, and chlorine +1. Among the all of acid, the oxidation state is higher of perchloric acid. That's why it will be the more strong acid comparatively all other acid. If the oxidation state are the same between two or more central atom, then the smaller size of central atom will be the more strong acid. Here I used two acid, nitric acid and phosphoric acid. The oxidation number of nitrogen and phosphorus are same, +5, but the atomic size of nitrogen is lower than the phosphorus. That's why nitric acid will more strong acid. pH and pH scale. You know, pH is the negative logarithm of the molar concentration of hydrogen ion is called pH. So pH is equal to minus log concentration of H plus. At the same time, POH is equal the negative logarithm of the molar concentration of hydroxyl ion is called POH. So POH is equal minus log hydroxyl concentration of hydroxyl ion. So find out the pH value of 0.001 molar HCl. So you know how to determine it. pH is equal minus log concentration of H plus. This concentration for only one proton. That's why we use 0.001. But here I use a shortcut way. If the concentration, in concentration, pH and pH scale. So pH is the negative logarithm of the molar concentration of hydrogen ion is called pH. So pH is equal minus log concentration of hydrogen ion. At the same time, POH is the negative logarithm of the molar concentration of hydroxyl ion is called POH. So POH is equal minus log concentration of hydroxyl ion. What is the pH value of 0.001 molar HCl? This concentration is given only for one proton. So H plus concentration of proton is equal 0.001 molar. So pH is equal minus log concentration of H plus. Putting this value, we get the pH is 3. This is the shortcut way how to determine the pH value of any acid. If the last digit is 1 and the all digits are 0, then pH will the number of all digits. Here there are 3 digits and the last digit is 1 and the previous 2 digits are 0. That's why we can say the pH is 3 of this solution. Again, what is the pH value of 0.05 molar sulfuric acid? Here the concentration is given for one proton. But we know if sulfuric acid is dissociated, it will give 2 proton. So the concentration of hydrogen ion will 2 into 0.05. So 0.1 molar. So its pH will 1 because after decimal only one digit is here. So its pH will 1. pH scale from ionic product of water. At the dissociation of water, it will dissociate and produce proton and hydroxyl ion. So this is the dissociation constant. K is equal concentration of hydrogen ion and concentration of hydroxyl ion divided by water. So the product of dissociation constant and the concentration of water, it represents the Kw, which denotes the ionic product of water. And at 25 degrees centigrade temperature, Kw's value is 10 to the power minus 14. So 10 to the power minus 14 is equal concentration of proton and the concentration of hydroxyl ion. Taking negative logarithm, we get it, and finally after calculating we get the equation pH plus POH is equal 14. For pure water, we know the concentration of hydrogen ion and the concentration of hydroxyl ion are same. So that's why H plus is equal 10 to the power minus 7 is equal concentration of hydroxyl ion. So pH is equal POH is equal 7. So that are same. Now what is pH scale? The scale that is invented by taking the pH value from 0 to 14 is called pH scale. So in pH scale, the range of pH value is 0 to 14. So you know, if pH is equal 7, that will neutral, and pH greater than 7, that will basic, and pH is less than 7, that will acidic. This mathematical problem is like acid. Here you have to find out the pH value of 0.001 molar sodium hydroxide. So we know sodium hydroxide is a base, so we will get POH from this equation, but at first we have to find out the POH value, then using the equation we have to find out the pH value. So its POH value is 3, and finally we get the POH value 11 by using this equation. Now the buffer solution and preparation of buffer solution. Buffer solution. What is buffer solution? A solution that can resist pH change upon the addition of small amount of an acidic or basic components. Again, a solution that can resist pH change upon the addition of small amount of an acidic or basic components. Suppose you take a solution whose pH is 3, but you add a small amount of acid or base. But if the solution's pH will remain same, then you can say that will buffer solution. So buffer solutions are two types: acidic buffer solution and basic buffer solution. If you want to prepare acidic buffer solution, you have to take a acid and its salt. Here I have used acetic acid and its salt sodium acetate. So preparation of buffer solution. You can prepare buffer solution by two ways. By adding weak acid and its salt, and weak acid with adding strong base. So you have to take acid, acetic acid and its salt sodium acetate. So these two solution, its concentration are same but volume are different. So you have to take the more amount of acetic acid comparatively its salt, then it will form buffer solution or acidic buffer solution. And you have to take a weak acid and strong base, and the amount of strong base will be lower comparatively weak acid. Here I use two formic acid and potassium hydroxide, where formic acid is weak acid and potassium hydroxide is a strong base, and the concentration of these two are same, 0.1 molar, and its volume is 100 ml and its volume is 35 ml, and this will reacts 1:1. I mean, here the potassium hydroxide's amount is lower, so 35 ml potassium hydroxide reacts with 35 ml weak acid, and in this solution 65 ml acid will remain in the solution. Then if that indicates the solution will acidic, and that will produce acidic buffer solution. A basic buffer solution are the same. You have to take a base and its salt. So I used ammonium hydroxide and its salt, ammonium chloride. So if you want to take prepare a basic buffer solution, you have to take a weak base and its salt, so ammonium hydroxide and ammonium chloride. So these two concentration are same and volumes are different. So the higher volume of ammonium hydroxide indicates the basic buffer solution. At the same time, if you take a weak base and a strong acid, you have to take the more amount of weak base. So it will also reacts 1:1, 1:1. So 25 ml, these two concentration are same. That's why 25 ml strong base acid will reacts 25 ml base, and in this solution 75 ml base will remain in the solution. That indicates the basic buffer solution. A mechanism of buffer solution. For acidic buffer solution, we have to take a weak acid. So we know acetic acid is a weak acid and it will partially dissociate and form acetate and proton. At the same time, we have to take a salt of this acid, so sodium acetate, that will be completely dissociated and form acetate and sodium ion. Suppose the pH of this solution is 4. If we add a small amount of acid like proton, then this proton will react with acetate ion and form acetic acid. And this acetic acid will not dissociate, it will remain in the solution. And if we add a small amount of base like hydroxyl ion, that will react with hydrogen ion and form water, and this proton will be lost, and the required amount of proton will be given from this acid, this acetic acid. It will dissociate and provide proton. For this case, the solution's pH will remain same. So this if the solution pH is 4, then pH will remain same as 4. For the basic buffer solution, we have to take a weak base, ammonium hydroxide, that will partially dissociate and form ammonium ion and hydroxyl ion, and this salt will be completely dissociated and form ammonium ion plus chloride. Suppose this solution's pH is 10. If we add a small amount of base, hydroxyl ion, that will react with ammonium ion and form ammonium hydroxide, and this ammonium hydroxide will not dissociate. If we add a small amount of acid like proton, that will react with hydroxyl ion and form water, and this hydroxyl ion will be lost, and the required amount of hydroxyl ion will be given from this ammonium hydroxide. In the case, the pH will remain same, and we can say the pH will not be changed in this solution, and it will 10. That's all your topic. This is your homework. So you have to complete all mathematical problems that I have discussed in this class. So you have to follow Hazarian Nag book